kind of single molecule transistors. After that, he did a postdoc in the Eisenstein group at Caltech, where he worked on 2DEGs. And so now he's kind of combining all these things and working on all kinds of cool stuff in nanotubes and graphene, and it's been really great having him here today. As theorists, bouncing some of our crazy theory ideas off him and having him tell us what's reasonable and what's not. So we're very excited for your talk. Thank you. Thanks for coming.
Yeah.
Thank you, Adrian. Thank you to everyone for inviting me. It's a pleasure. Thanks for taking the time. I know that you have a lot of things to do. So our niche really is to think of the combination between electronics and mechanics. What are the intersections? And to do this in systems that are extremely clean, so that they're both sort of easy to model, so we can get an intuition as to what's supposed to happen in terms of quantum mechanics, and also that they're experimentally, it's achievable, in fact, to make them very clean, to make them very sort of idealized in terms of having very little disorder and being extremely good and tunable in terms of mechanics as well as in terms of electronics. So this intersection of this playground that we found that works for us is carbon nanotubes and graphene, but there are many other possibilities. Just the one we perfected. It's not so much just about the material, then what's the physics therein and the very high tunability that we can access. So I tell you, so at this diverse crowd, and I didn't know so much of the department, so I try to cover all the bases in terms of having a few things that are a bit more advanced and a few things that are a bit more introductory. So I start by saying, okay, why should we use graphene to do this kind of idea to couple quantum mechanical ideas in terms of mechanics and in terms of electronics? And what kind of devices, let's say proof of principle devices, we don't do extremely applied things, but we try to build up ideas that could be used as devices. And how do we sort of model this in basic terms? And I'll tell you about a few experiments we completed recently. Basically, we were able to make very small devices where the electrons are ballistic, so basically preserve their phase as they move across the device, their quantum phase. And they also not just preserve their phase in the device, the channel, if you wish, also in the contacts, they are ballistic there. So we can really think of phases of the electrons and think of quantum mechanics. I'll show you an example of an effect that happens when you scale things down. So the idea that we don't just make graphene and nanotubes, which many people do, is we try to make them at smaller length scale than others. This brings up the energy scales for electronics and for mechanics, and it changes some of the interaction, it changes some of the things you can observe. So that's our niche, right, to make super clean and very small devices. And in nanotubes, we'll show how we can build, for example, big asymmetry between moving holes in the system or moving electrons. And if you build two devices into a single one, two quantum devices. I'll also say a few words about how we can measure not only how electrons carry charge, but energy in these systems. Then I'll conclude with this. This is mostly about electronics, and the idea now to introduce the mechanics. I'll show how we can make extremely high-frequency resonators. So by sending electrical current, actually you can activate the mechanical mode, and you can sense that. And so this is the idea of sort of time-dependent mechanics, if you wish, vibrations. And I'll show you that what we're working on right now also is sort of DC, if you wish, mechanics, time-independent mechanics. By applying strain, you can modify quantum electrons, how they flow in the system. So first, some introduction. So the idea of experimental quantum electronics is, we really want to make things, we want to remove all disorder. So we have three basic things that we want to do to remove all disorders. To have a cold system, so you don't have thermal fluctuations, thermal excitations, which is basically noise. We want to make things small, so there's no spatial disorder, right? Here's a famous example where things are small. You can think of each atom. Those are actually, it's STM image. It's not for us, of course, but it's the STM image of individual copper atoms. And the fringes in the middle are actually electrons that are shared by these atoms. So when you make things small, you can actually make sure that there are very, very few defects, right? Things are clear. The same idea of a single molecule. You can know where each atom is. So small, cold, and clean. By clean, I mean you don't want to have anything, for example, absorbed on the surface of this molecule, right? It could be a water molecule sitting there, or a dangling bond, or something like that. So these, and this is a cryostat, we would cool things down and we can apply in different fields. So this is doable in these carbon systems. And the gist of, so what do we measure, is more or less, we want to measure the Hamiltonian of the system, right? So you'd like to be able to write this equation to describe the energy of the system. It's a matrix, you diagonalize it, you get the eigenstates, right? So that's the beauty of these materials. They VR quantum simulator, they can only solve the one Hamiltonian. They solve their own Hamiltonian, but it's a very big system, so it's a beautiful thing. So we like to, with this sort of system, be able to tune it. For example, by changing the number of electrons in the system with a gate electrode, we can apply electric field that's perpendicular to change the number of electrons. And with this voltage here, we can excite, we can inject high energy electrons to create excitation in the system. So by doing these things, so with this you can think we're changing the ground state of the system, and with this we can either probe the ground state or create excitation. So an example of, now we want to measure the position of the energy levels. So the solution to the Hamiltonian is where are the energies of the Hamiltonian. So that's an example here. In this case, you can think of a barrier at the interface of this tube. It makes a box, and this box has discrete energy spectrum. And depending if you have, mechanical excitation, electronic one, or magnetic ones, they will have different energies. Now, this S means the source, and the D is the drain. And you can now apply a bias between the two, so that's the actual bias you're applying here. So if you have an energy level that falls within that window, actually there's electrons can go in, so you're going to have some current. So it will see a click, and in this graph here, if we're talking color and conductance, how much current we get versus the bias, so this energy window, and the gate, which is moving the ground state, adding or removing electrons. When you have white, basically there's no current flowing, so you don't have an energy level in this window. And when you have colors, current is flowing. So then, when you have these specific points where current turns on, you can actually measure the position of these levels. Okay. There are many details to it. In fact, if you look in the red and the blue region, is where you can see the excitation, and over here are the ground states. So the numbers refer to the number of electrons on the dot. Okay. So the idea is you can measure, you can create these zero-dimensional system, one-dimensional, or two-dimensional, and measure their spectrum. So why do we want to do this in carbon? It's the bonding in the plane of the graphite, right, in the single layer, which is graphene, is extremely strong. So in fact, if you do STM, you'd have a very hard time to find a defect. They're tough to find, there are very few, so disorder is not a big problem in terms of the lags. Then there's a lot of fun. Also, there could be edges problem, but what we can try to do is remove the edges. I'll tell you how. Either you roll up this into a cylinder to get rid of the edges, or you just make it very wide. There's also a lot of intriguing physics, because it turns out that in the system, the equation of motion basically is linearly related energy and momentum. So it's different than the usual, which is the Schrödinger equation, energy is momentum squared. So here, it's more similar to relativistic physics, particle physics that would happen at very high energies. So there's all kinds of new scattering mechanism, for example, between electrons and phonons, so there's new devices you can build. And one especially cool thing is that this is an extremely strong mechanical system, and it's also a very good high mobility electronic system. So we can place these ideas how, if we deform it mechanically, we can control the quantum flow of electron, and vice versa. If we apply electric field, can we change the mechanical modes of the system? So there's potential for the application in terms of sensors. You can make transistors. I'll propose one at the end, which is a strain transistor, where in graphene, you see this is the dispersion relation. There's no band gap. There's no forbidden energy, and that's bad for making a transistor. But I'll show how with strain you could actually potentially make a very good transistor. You could also think of heat transistor, where you can turn on and off the flow of energy. In a nutshell, here are the big differences between a sort of standard two-dimensional system, the semiconductor, versus graphene. Is the energy here is linear momentum, so you would want to use, for example, the Dirac equation as opposed to the Schrödinger equation only. So then you actually want to describe this as an effective mass zero fermion. And there's no band gap. So here you can see this one is a cone. You'd have another cone down here somewhere. There would be an actual gap between the two. And another point which is sometimes forgotten, but is very important in terms of electronics, is that the density of state, the number of states for the electrons at each energy, is actually different in graphene as a function of energy. So there are more states at higher energy and fewer at lower energy. It goes like E. But in regular 2D, it's a constant. So there are as many states at any energy. So that changes a lot, actually, the coupling, for example, between electrons and photons. How would we actually write down the Hamiltonian for graphene? The sort of back of the envelope starting point is to think of a tight binding Hamiltonian. What that means is that you say the electrons are really tightly bound in carbon, so you start with the orbital from just carbon atoms, right? So you think of the S and the P orbitals, and now you say they're going to be disturbed a little bit, so that's the Hamiltonian, just the so you know the solutions. And you use perturbation theory, we just say, there's a small probability now I'm going to actually move to the next atom. And these are just operators to destroy, make the electron move from one side to the next. Okay. So then you just diagonalize this Hamiltonian. What you'll get is bands that look as such. And so at the top is the conduction band. This is usually empty. And at bottom is the valence band. You can think of it as molecular orbitals. This would be like, let's say, the s orbital of the big molecule and the p of the big molecule. And really the Fermi level, which is the natural energy where it lies, is at this interface between the two. So there's only 6 points where actually the energy levels touch. And these 6 points, if you zoom in, they're like linear cones. And basically, to achieve this region, to enter this region of the band structure, you need very high doping to put lots and lots of charged carriers in the system, which we don't do. We deal with a clean system. So we always work here, and we always can think of the energy dispersion of graphene as linear. And there are 6 of these magic points, but by symmetry, actually, they're related 3 by 3. So there are only 2 that are fundamentally different. There's one we call K and K prime. So it means for any energy, there are 2 copies of every energy state. You can have an electron with energy E1, let's say, in K prime value, and 1 in the K. So you always have a factor of 2 in transport. And there's another factor of 2 because you have 2 bands. And basically, it's from the fact that graphene is made of the 2 atom bases. You have the yellow and the blue ones. And there's a quantum number we can introduce. If the electrons are on the blue lattice, we say they're, for example, in this case, pseudo-spin up. And if they're on the yellow lattice, the pseudo-spin down. And you know by symmetry, there actually are both on both lattices because the atoms are identical. But that means that pseudo-spin is in the plane. However, you can't specify which angle it has in the plane. Right? This is what we mean by pseudo-spin. And this is actually a conserved number, that phase between the wave function that's on the 2 lattices. And whether that phase will be aligned with the momentum of the electron or anti-aligned is actually a conserved quantity in graphene. So that's called a pseudo-spin, right? So it's aligned or anti-aligned, we'll call that pseudo-spin up if it's aligned with momentum, and pseudo-spin down if it's anti-aligned. So that's how you can map the graphene problem onto the Dirac sort of high energy physics. In high energy physics, when you have a Dirac equation, usually things travel close to the speed of light. Okay? In graphene, they don't, but you basically replace the speed of light with basically the velocity of the electron, which is called the Fermi velocity. And usually you have a mass threshold, but there's also an equation for zero mass particles, which is a Dirac-Weil equation, and that's the one we use in graphene. This one will be useful, for example, for bilayer graphene, when there's a mass threshold. And finally, you have linear relationship now. You have a single Bell operator, so it's a linear momentum. And you have the pseudo-spin is dotted with that. So the orientation of momentum and pseudo-spin, that alignment actually matters. In relativistic physics, usually it matters because if you're traveling close to the speed of light, the particle creates its own magnetic field if it's charged, right? You have to boost the frame. So the alignment of your spin with that magnetic field, electromagnetic field, matters. Now, we're not really traveling the speed of light, but we have something equivalent, the pseudo-spin. So the alignment between the pseudo-spin and the momentum matters, and it's conserved when you scatter and when you move around. So that pseudo-spin now gives us also, another degree of freedom, and that's the beauty, is that we'll be able to manipulate, for example, that pseudo-spin with mechanical strength. So because it's a quantum degree of freedom of electronics, but it can be tuned with mechanics. So we can think we have 2 components of the wave function in each valley. We have, pseudo-spin up, if you wish, and pseudo-spin down. If you went to the holes here, pseudo-spin would be anti-aligned. And you also have 2 valleys, so you end up with 4 copies of every electron state. And basically every electron is in a superposition of electron and hole. So if you look at the wave function, you really have to have a 2-component wave function. If you include the 2 valleys, it's actually 4 components. So that's the same thing as if you include spin in the Schrödinger equation, you need a spinner, right? The 2-component spinner. So this is actually the wave function, and this is just then a plane wave times the spinner, which has to do with electron and hole part of the wave function. Or you can think of it as matter and antimatter if you were in quantum physics. So if you actually try to scatter electrons off of a potential wall in graphene, there's something very interesting happening. Pseudo-spin has to be conserved. But think of it now, the particles in graphene are both electron and hole at the same time. They're in a superposition state. So if you have a potential step for electron part of the wave function, it's actually a potential well for the whole part of the wave function. So they're unstoppable electron in that sense that you will simply transfer from being an electron-like to a whole-like particle when you get to the step, and then go back to electron-like on the other side. So you would think that transmission should always be one in these systems. It's called the Klein tunnel. But it turns out if you look in the details, this is only true when you come at the normal incidence at zero angle to the boundary. If you have an angle, you can get reflected. Basically, transmission here falls to zero even at some point. So this is very much like optics, right? Optics, you have linear relationship between energy and momentum, and depending on the index of refraction between two medium, you can get reflection. So here, basically, you can reproduce the same thing with some angle reflection. So let's say now we assume this is true, and we want to calculate what is the actual conductivity of a piece of graphene in the quantum language. So the simplest model you can think is, okay, it has a finite width, and for each finite width, right, there's a quantization of the transverse momentum, the ky, and so those constitute a single mode of transmission. There's one electron, let's say, that can fit across this graphene flake, and that's one mode of transmission, and then I can think of a second mode, a third mode, and so on. That sets the bound, the quantization for the transverse mode. And then you can think of, how many modes you're trying to inject from the leads, basically the piece of metal that's over here. And by matching the wave function in the graphene that's underneath here and the one that's here, you can come up with a transmission function. The details don't matter too much, but what I wanted to point out is this mu is basically the chemical potential in the graphene. So basically, if you dope it more or less, you can have more or less of these modes that basically, this ky is quantized, right? So if you have very little energy available in the system, and this is a big number, then you can see that the kx has to be imaginary, because the total k is the energy, right? So then the mode in kx will be imaginary, the transmission goes very low. You can think of this as being a very big angle, so like a 90-degree angle is reflected. But if you have a very high energy in the system available, then even you have some ky, kx can be real, and then it's a transmission load. So those actually tend to have a lot of kx and little ky. They have a small angle, and transmission is actually close to 1. So you would think of each of these modes and find a transmission, and then just simply add them all. So from all the modes that matters, you sum them, and you get an equation, basically a transmission total conductivity like this. And you see V gate here is actually tuning this number, the number of modes in the system. And these steps is basically when each time you open a new mode, you can see one. In experiments, you don't usually see these steps because you have some mode mixing the interfaces and all. So that's the gist of how you can think of this. But why I wanted to say this is to introduce how strain couples in this idea. So we can rewrite this the same Hamiltonian as before. You see this pseudospin dot momentum, but I added two basically electrostatic potential. This is a real. If I strain a piece of graphene, two things can happen, right? I'm changing the area within these hexagons. That's changing the density of electrons per unit area. That's a real potential. But I'm also changing the length of the chemical bonds, and that will change the tunneling matrix element. And turns out it can be mimicked perfectly by a gauge field, just adding a pseudo magnetic field, a vector field, and it couples the pseudospin. So basically, strain is to pseudospin what a magnetic field is to real spin. That's my point. So you could be in real magnetic field 0, but if by applying strain, play with the pseudospin of the electrons here and create similar quantum effects. Okay? So that will be our gist. And one prediction from theory, for example, is that the conductance that I just showed to you here, you see it's quantized, it never goes to 0 because of this idea of Klein tunneling, for instance, right? So it's 1 times this quantity. It can be turned all the way down to 0 with some finite mechanical strength by this prediction. Turns out this prediction is not quite correct in terms of experiments, but it's a good intuition to go that way. And the last point I want to make about this is you can actually go further and think of now the strain as being time dependent. So we know that in E&M, if I take, let's say this A field as a curl, it's a B field. Now if it's time dependent, that creates an E field, right? It's Faraday's law. So actually, phonons are nothing but a time dependent strain. So I can understand now the electron-phonon scattering from that point of view. So I can think of strain as being the mechanism to couple electrons and phonons. And there's also other kind of coupling. It has to do with the real the area of the system. So to summarize, what are our goals? Okay. So we want to make extremely small systems that are very low disorder. They have rich Hamiltonian that we can tune, and we'd like to have them, clear mechanical modes and clear electronic modes. And we want to do this usually at small scale where the energy scales are pretty big. Some of the applications or motivations in terms of concrete problems. So one of the ideas, for example, is in graphene or in carbon nanotubes, things are quantum, so that's cool, right? But you also want to make pretty small devices if you want to think of a quantum transistor or a qubit or something. And one of the problems with this is the size of the device is limited by the size of the barriers you can create in the device, the p-n junctions which are necessary to build transistors, for instance. And usually, if you think of very clean graphene, it's done in suspended graphene. So you have to have a spacing between the gate and the graphene, and that length scale limits the width of these junctions, right? If it's 100 nanometer away, it'll be roughly 100 nanometer wide. So the point is, what we're trying to build is much smaller devices. For example, we can use a metal film directly on top of graphene as a gate. And I'll explain how that works, but basically the electrons here, they stay in the graphene, they don't go in the gold. They'll go in the gold only over here to stay in the graphene. And it makes very sharp p-n junction at the interface because the spacing between the gold film and the graphene is very tiny compared to this air gap here. So you can scale down devices, that's one objective. If you scale them down, you can also make extremely high frequency resonators, because resonators, the frequency scales with the length 1 over L squared. So high frequency means sensitive devices or quantum systems. And in terms of now DC strain, one thing we're trying to do is what I explained in terms of the strain transistor to turn off the current flow without a band gap. In the longer term, one thing you can do with more complicated strain, if you pull in 3 directions, instead of applying a constant A field, right, a pseudo vector field, we can apply a pseudo magnetic field. In fact, with a 3-dimensional strain like that, it's almost a completely uniform pseudo magnetic field. So you can really create what's called Landau levels, just like a real magnetic field. And these Landau levels, you have all the quantum Hall physics and so on, but you can do this in 0 magnetic field. And of course, you can combine then the pseudo magnetic field with the real magnetic field and create new phases. You can also achieve in these very small devices basically an interface between the idea of molecular electronics. In molecular electronics, you want to make a single molecule as an active element. The problem is you don't control the structure of the environment very well. So here we can do small, but with still having crystals we know the orientation of, we have very few defects in, and they're tunable, which usually they're not in single molecule. So we want to make them small enough so we approach the kind of physics energy range of single molecules, but keep them tunable. And an example here of preliminary data we have is where we can see strong electron-electron correlations. It's called Kondo physics, and also excitations that have to do with the mechanics. So you can both have many-body electronics and in some way many-body mechanics, and you make things like polarons. So there's fundamental ideas to be studied in that realm. So in terms of what we did so far, because we're on our way, but we haven't done everything, is okay. First, how do we actually build devices? How do we connect such small things and flow current in them? An example here, it could be a nanotube on a surface. We build basically a grid to know where things are. And we can also have crystals made of single layer or bilayer graphene, for instance. Then we just find them and we build devices where we found the crystal, right? So in this case, we put a piece of gold right on top of the nanotube, and then we etch the oxide underneath to suspend the gold. So what you want to think of is a nanotube with a film of gold on top, and both of them are suspended. Then later on here, you have big contact pads that look like this, and you make little solder to them, and then you can flow current through these devices. And if you flow the current the right way, you can actually just electromigrate, move away the gold atoms, and reveal the little carbon nanotube channel. So now you have the source, channel, and the drain. So this one is pretty big, so you can see it, but we can make it at any more or less net scale. Here's an idea of the alignment, right? So when we try to, so this is an overlay image. This is after we do the lithography, and the nanotube is before, and you can see how basically we can build different devices just on the same tube. What's really cool here is because it's the same tube, it has the same rolling. So in terms of the physics, you know how to compare these different devices. And this is the geometry that we have. So we have a central channel, then we have suspended gold films that will actually act as doping area. And then you have the two continuous over here, disordered areas where really the electrons are transferred from the gold into the tube. So that's what our devices look like, and at the back here is a gate to apply electric field. Okay, so how the last point is how to actually build, I didn't tell you a lot about how you can actually open up this gap. We have basically a procedure where you apply electric field across, and as you see, you monitor the resistance of the bridge. And once it starts to basically decrease, well, the current decreases, so the resistance increases, you know that it's starting to etch. So you don't want this to explode, to be an avalanche process. You're going to ramp down the voltage and then back up and down. And with these ramps, you can basically etch away this into a narrow section, and then eventually just decide when you break it to open up gaps at different lengths. So if you use more power when you break it, you make a longer device or a shorter device. In this case, it was 14 nanometer, and the tubes are very strong, so they're not damaged in this process. We can do this also with graphene. I didn't talk a lot about nanotubes, but the one point I want to make is it's the same as graphene, except that when you think of the first Brillouin zone or the band structure, it's a bit like you're making cut in the band structure. So depending on how you roll the tube, you can either have the same dispersion as in graphene, or you can have a band gap. So it's interesting in that sense that in tubes, you can have band gaps. So here's now a first set of experiments we did on nanotube. And what we think of is this geometry again, and I already went through it. Over here, basically, we have this ordered system where the electrons are mostly in the gold, and they are injected in the tube. Over here, what we'll see in a moment is they move ballistically in the tube, and then they enter the channel, which is at a different doping value. And in terms of what's interesting, in terms of what we control, here is the central channel, and this one is the density, so the Fermi level here is movable with a gate. And this Fermi level here is not movable, it's fixed by the gold film. Right? But the actual value of that position depends on how much oxygen is in the gold film. So this actually when we do this electromigration to open up the gap, it turns out that we bake the gold and remove the oxygen, and it usually makes it N-doping. If you then add oxygen by warming up the system, you can also make these regions P-doping. So it's just to say that we know we can control how much doping we're doing in the contacts of the channel. So if you think of it now, depending on where this band's going to have to align, when actually these two sections are touching, the Fermi level will have to align, and you might get either a barrier forming between the two or not. So if you think, of course, you make this Fermi level perfectly aligned here, then there won't be any barrier. But if it's down here, there will be a barrier. So that's what is happening in the system, that in this case, if you p-dope the system, you have a tunnel barrier for the electrons coming from the leads to the channel, but you don't if you actually are N-doping the channel. And in experiments, this is very dramatic how it shows up. In the same device, if you just change the gate voltage, you can go from something that looks like a quantum dot. So again, these diamonds mean ground states where you have a fixed number of electrons on the central channel. So it's a little box. The box is 100 nanometer long. You can get that from the width of the diamonds, for instance. On this side, it's really a Fabry-Perot difframeter. So those are interference fringes. You can see here the shape of the fringes. But they really just are electron waves bouncing back and forth. And from the spacing, you can get the length of the interferometer, and it's the length of this one here, the white arrow. So basically, when you're, hole doped, well, in this case, electron doped, you actually bounce back and forth between these two ends. And if you're hole doped, you're just in a small dot. So in the same device, we can tune between a quantum dot and a ballistic bus, if you wish. So you could eventually think of making qubits, for instance, and you're having interconnects and interrogating. We can do this in also shorter devices in very small quantum dots. So on both sides, in this case, whether it's hole or electron doped, they're quantum dots. But the point is the height of the diamond is the energy scale. It's called the charging energy. And this charging energy can vary by up to a factor of 2 or 2.5 depending on the doping. So if you think of those in terms of detectors, for example, for radiation, if a photon comes in and excites an electron, you would detect it. Well, you'd have two detectors into a single device, two charging energies. And the sort of sharpness of the PN junctions that we can create at this interface here is actually of the order of 2 or 3 nanometers. We also do the same thing with graphene now. So in graphene, we can also make very small devices. We suspend them in the case they're bow tie shaped, and we electromigrate them again. And it makes very short channel. This one is about 6 nanometer long. We can make them a bit longer, and we control the length with the power at which we break the device. When they're very short, one issue is that you actually are doping the channel with the contacts, so you don't have as much tunability as for the device. But as soon as you exceed about 20 nanometer, you have a lot of tunability in the device, and it turns out that they're great to map out the Hamiltonians we're interested in. Similarly to what we saw in nanotubes, actually the conductivity of these devices matches what you expect for ballistic electron transport. So all I'm showing here is the conductivity, the resistivity, the inverse of conductivity, is close to quantum of resistivity, which is what you expect for an undoped, pristine piece of graphene. So if we want to really model this with the initial model I showed, the quantum calculation of what's the conductivity versus gate, you want as well as you can control geometry, right? So these geometries are not perfectly controlled. You see they're a bit rougher, the shape of the contacts. So we can make bigger devices here. In this case, it's about 100 nanometer long and a micron wide. And basically the measurements match very well with the theory. Okay? The additional, you see there are additional bumps in the measurement. But that we already understand because they are not from the channel, they're from the contacts. Remember, the contacts are also ballistic, and when the electrons bounce back and forth, they create interference fringes. And those are these fringes. If you measure the spacing between them, they actually give you this length. And you can tell that these contacts are annealed because if you look at the texture, also the gold film texture is different. So here the gold is really sort of annealed, and here it's not. And it's simply because this is not thermally anchored. So when we flow big current in the device, this gets hot. This doesn't get hot. So we can make these ballistic devices, and by measuring the position, the spacing between interference fringes, you can actually get the length of these cavities. So for instance, these small fringes here, 4 milli-electron volt, they correspond to the length, the suspended length here, the 500 nanometer length. And for the 100 nanometer channel, this length, you can see it as well in 22 milli-electron volt spacing between. And if you turn off the temperature, then these resonances go away because you're scrambling the quantum phase. It's not coherent anymore. We can also tune not only the length of the devices, but the width. It turns out if you use different power, you can create very symmetric shape in the electrodes, and this is actually a controlled process. And you can think of this as a finger, right? And now you can apply fields to rip the graphene and make narrow channels. When you make narrow channels, you can have open quantum dots. In this case, you see Fabry-Pro interferences. Again, the point is that this device is ballistic, and you also have ballistic contacts. So these interferences are from the contacts. And if you actually make them narrower, you can also make quantum dots. So the width boundary condition here can open a gap in graphene, and you can see that in transport. Okay? So if we make different devices at different width, and we look at the resistivity, we see that we control the resistivity, and the shape of the transport goes from something that's ohmic to something that's nonlinear and looks like a quantum. So you can basically make zero-dimensional systems where it's like an atom, or really a two-dimensional flat system that's a 2D. So we saw ballistic charge transport, but can we also see ballistic energy transport? So that's what we did in this experiment. We wanted to know, okay, the energy carried by electrons is called the thermal conductivity, the electronic thermal conductivity. Usually in graphene, the phonons carry a lot more heat. So actually the electronic thermal conductivity is really tough to extract. But one trick that we found is that in the right parameter range, in very clean graphene, it turns out that the electron and the phonons, they are decoupled. There's very little scattering between the two. So we thought, okay, if we can heat up the electrons, and if they don't have time to thermalize with the phonons, we can just measure how much heat the electrons carry out of the system when they go to the leads. So that's what we did, and this has application, for example, in photoelectronic devices. If you shine a photon and you want to create electricity with it, you better make sure that the energy that you heated the electrons with doesn't go to the phonon, because you want the electrons to reach electrode to generate electrical current. So if you understand how much heat conductivity you have in the electrons, you can know if you're going to have a good or not photoelectric cell. So we can make larger devices in these systems because we need to, those are details, but in terms of modeling, we need the electrons to thermalize with each other, right? So we need some length scale where the electrons have enough time to thermalize, make a fluid that's in local equilibrium. Again, we have a transistor, so when we're close to zero gate, we have no doping in the system. We go on one side, we can add holes per electron. And here we're just showing the initial condition of the system in the red curve. And if we flow big currents through this, we bake it, and it basically gets cleaner, and you get the black curve, which is very close to the empirical one. So the idea that why the experiment worked well and was simple was that the graphene was its own thermometer and its own heater. So to heat it up, we simply flowed current through it, and it got hot. And because we did the very detailed calibration, we basically, by applying a bias, we could measure temperature going up. By measuring the resistance, basically, you know the temperature of graphene. And if we, well, that's the example. It shows here how the resistance changes with temperature. And then to extract the thermal conductivity, basically, okay, how hot does it get is telling you how easily the heat goes out. If it gets very hot, it means the heat didn't get out very easily. And if it doesn't get very hot, even though you're applying a lot of power to the system, then the heat got out. So to solve this is a simple 1D heat equation in this case. And the data matched very well with theory. And it basically told us that the heat carrier were also Dirac particles traveling at the Fermi velocity. What was interesting also, this was done close to the Dirac point, so zero doping. And then we did experiments at finite doping. And what's interesting, because you can add or remove electrons, you can tune how much heat flows in the system. So it's a bit like a thermal transistor, but in the case just for the electron part. We can think later of also doing the same thing with phonons. And again, you could modify phonon modes with strain. So with strain, you could actually change a lot the number of phonons in the system and eventually do something similar to this, turn on and off the heat flow from phonons. There are different things predicted in terms of extension of this work, but because of time, I'll go to the following part, which is, okay, now we have a quantum system where we can see quantum transport of electrons and holes, but can we really couple these? We also showed how we don't want to couple them in some cases to the phonons, but can we couple them to phonons or to any other mechanical modes? So we did both big and we do both big and small systems. So in terms of big systems, we're interested in bilayer graphene. So monolayer graphene for big flakes has been done quite a bit. But for bilayer, people have looked at them and basically look only at the mechanics, and they look only at the electronics. But very few people, to our knowledge, pretty much nobody, has looked at the electromechanics of bilayer. And why they're interesting, for example, is that in bilayer graphene, there's no band gap, just like in graphene. But you can actually create the band gap with just a perpendicular electric field. So one of the ideas, if you can create the band gap with just a gate voltage, and this, you can think now of this as an oscillator, mechanical oscillator, you can say, well, one way to dissipate energy for this oscillator is to flow currents. But if I have a band gap, I should be actually removing that way of dissipating energy. So I should be able to tune, for example, the dissipation of the system and have a tunable quality oscillator. There's also nonlinearities in terms of mechanics that should be very interesting. Another thing that we want to do further down is we want to use the mechanical resonances to probe electronic phase transition. If you have different liquids of electrons in the system, then the way they carry charge is different, and the way they couple to the mechanics will be different. So you should see change in the quality of the mechanical resonance as you do different phase transition. So how did we detect this? It's quite simple. It's something that was done in another system. What was different in bilayer was a technical achievement that the idea is to mix two signals. So you apply a radio frequency signal on the gate and one on the source, and they're slightly offset in frequency. And just like any two sounds that slightly offset in frequency, they make a beat, right? So the offset in frequency, which we call delta F, creates a beat, and you can measure this as a current going out. It's called the mixing current. How strong that is basically depends on, it's called the mixing. And this has to do with the fact that the conductance of the system is non-linear, right? It's basically, it changes as a function of gate, but it also changes as, okay, either you have a gate voltage that's changing, or you can change the capacitance. So if this is vibrating, clearly the capacitance is changing. So then you're going to change the conductance, and that will mix these two frequencies. So if I have a mechanical resonance, I'm going to get a lot of mixing between the two. And if I look at the mixing current with this Lockton amplifier, I'll see a big spike at that very precise frequency. So that's a detection of mechanical mode. And there's really no other thing in the background. And in this case, it survived up to high temperature. What was the challenge in bilayer is that the mixing, the amount of mixing is very small because the conductance is much less dependent on the gate, basically, than in monolayer graphene. But what's interesting is it's a completely new material to explore. And what we showed also is you can tune the frequency of the oscillator with gate, so you just stretch it, and you can make very high quality oscillators. And you can also drive them pretty hard and do what's called nonlinear dynamics. So in this case, it's a so-called Duffin oscillator. But the point is that it's a good system for further study, but that's not as far as we go. So this is the big oscillators. We can also make very tiny oscillators. And in this case, there's a small tube here. It's not easy to see, but this is the signature. So if what I showed you before is a quantum dot picture, this is n electron on it, n plus 1. In this region are the excitation spectrum, right? The excitation of the ground state. And these parallel lines that you can see, each of them actually, the spacing between them gives you the energy of the mechanical stretching motion of the tube. So we can measure there the phonons, the stretching phonons. And the energy matches correctly the length of the device. Now what we can also measure is the out-of-plane motion, the bending mode of the device. We call them vibrons because they're actually they're quantized with a different boundary condition. But anyway, the vibrational mode like this. And the way we monitor this is with again, the same sort of diagrams. You can see sort of a blur here, but if you clean the system, you anneal the system, so you basically improve the quality of the oscillator, you start to see a very sharp resonance. And if you go inside the Coulomb Valley, basically in this region where there's no current, the only mechanism to flow current now is to actually move this, right? If you think of moving this closer, you're changing the gate voltage, effectively you can suck in an electron. As it comes out, well, you can think of an image charge you're copying in and out, right? So that you got an attractive force each time an electron goes in. So basically flowing electrons triggers mechanical motion. And the mechanical motion can suck in the electrons. So it's a cascade, basically positive feedback, and it can lead to really high amplitude resonances, and that's what we see in the current. We see that if you look at the IDD, you see very sharp resonances in the transport, and the frequency of the current matches the bending mode from the length of the system. And in this case, they're 80 gigahertz, and we could do even higher frequencies. We saw something similar, although this is unpublished in graphene, because there we don't have sufficient data to see it, but basically in small pieces of graphene, we think we also see these mechanical modes at about 100 gigahertz, but the data is not as conclusive so far. So we could use strain, for example, to tune these systems. There's also new physics that is achievable, for example, in carbon nanotubes. If you have very strong coupling between electrons and vibrons, it's predicted that the charging energy of a quantum dot could be changed. And it could be changed so much that the charging energy could basically become negative for some of the states. And what that means is that you could, for example, for odd states, odd number of electrons, have very small charging energy and very big one for even, and even have it go pretty much to zero for odd states. So this is preliminary data that we have where we think we observe this effect, and it's basically from the coupling between the stretching phonons and the electrons. Okay, so this is something that's predicted for single molecule kind of systems. And because we have these very small 10 nanometer scale nanotubes, we think we have now a system where we can achieve this, and it couldn't be done before. So it's a very old prediction, but it has never been seen so far. So hopefully we'll be able to confirm this. And now the last piece is this DC mechanical control of the system. So here, instead of doing time-dependent strain fields, the vibrons, we're trying to build a system. Can we apply a strain in graphene, which we said, or in nanotubes for that matter, which we said really mimics like a gauge vector field. So here the system is, think of this as your gold electrode on top of graphene. This is the freely suspended part, and here's the other one. And we have uniaxial strain, which means we just pull in one direction. In the center here, there's some finite strain, and here's no strain. At the interface, you have a momentum boost in the ky direction. And how much that is simply due to this strain. Okay, so the actual strain is, it looks complicated, but uxx is the pull in the x direction. That's the only one we're applying. We neglect this one, and this one is zero. So basically, it's just that. There's only an A field in the x direction. And how much there is simply delta L, how much you elongate over the length. Right? And then now you put this in the Hamiltonian, you have the minus, instead of just k, you have k minus A. And that minus A is basically, in this case, the AY position. Okay, so you'll basically be able to tune the angle at which the electrons propagate in the system. So the proposal that we were trying to realize is the idea that now with this, we could actually turn off, basically create complete reflection of the current at the second interface. If they come at a big enough angle, I told you, depending on the angle, when you hit this interface, you'll be more or less reflected. So if you have the right amount of ky boosting, you could have total internal reflection in the second interface. So there was a prediction that this is possible way back in 2008, but basically what they were assuming is that you had the same Fermi level in the graphene underneath here and the graphene here. And experimentally, that's not really feasible because how would you create a sharp strain difference between these two and still have the same doping? Anyway, we're not able to do that. So this is not something we'll observe. Now, the other prediction that was done by Torzidlo, which is the calculation I showed you earlier for transport, is that the leads here have infinite chemical potential. And that's actually not a bad approximation to some limit. But if you do put that in the strain model, you get actually zero strain effect. If you strain the system, there's nothing happening. But luckily enough, in our system, the chemical potential is not infinite in the leads, and it's also not the same in the channel. There's an offset, but just about the right scale that we think we can see the turning on effect. So how did we measure the chemical potential in the leads? Is by going back to this calculation by Torzidlo for what is the transmission that we expect. And we basically, as we anneal our system, well, we flow big currents to bake this off. We can change the amount of oxygen content in the leads, and we can change the doping underneath the leads. So in this case, and we then compare with the calculations. So if we put delta phi 75 millielectron volt in the calculations, we get the dashed red curve. And the data that we're trying to match is the full red curve. And if we put, this is negative, and basically electron doping, and this is positive for hole doping, at plus 90, then we get the black curves. So there's very good matching, and you can see that there's left to right asymmetry that's flipping, depending on whether you're doping with holes and electrons. And it makes sense because the barrier, the p-n barrier interface is different, right, for the two cases. The point is that this chemical potential in the leads now is the order of 100 millielectron volt, and it's also tunable, something we can tune. So to really make prediction as to what's going to happen with strain, that's the number we want to put into our theory. The other thing that was absent from the other models is that the angle of the strain matters because only the strain along the zigzag direction of the graphene matters. So since we don't, in our experiments, control the orientation of the graphene, we can basically have a varying angle. So it can be, on average, square root 2 over 2 effect, but we need to make multiple devices to see that. So what is the outcome is this. So this is our calculation for what happens with strain. So if you start with the blue curve, that's on strain, with 100 millielectron volt lead doping, like we have in an experiment, you get the following effect. So you see, if you apply something like 1.2% strain, you completely turn off the conductance. But what's especially exciting is that it's turned off only for some gate range. Meaning if I can create a system where I have this strain in the graphene, for example on a substrate, then I can just use the voltage now to turn on and off the graphene. But it's pristine graphene, there's no defects in it. It's really a quantum mechanical reflection at the interface. And we built a quantum strain transistor. So that's what we're trying to realize experimentally. The challenge though is that you can see that not much is happening actually up to 1% strain. And all the action happens around 1, 1.2. And again, that's assuming that all of the strain is along the zigzag edge. So if you're not perfectly aligned, you might have to apply 2, 3% of strain, which is tough to achieve experimentally. So how do we do this in terms of our setup? We build the following instrumentation. So you can see you just have a screw that's going to bend the chip. On the chip, we've got a suspended device. Basically, everything we've done so far is building up to this. The idea is to make devices that we understand every single detail of, so that when we put the strain in, it's the only thing we're trying to explore as opposed to understanding everything else. So then the strain here is only applied from the screw, actually. If you apply a gate voltage, because this is such a short device, it would just be 50 or 100 nanometer, in this case it's 100 nanometer, the strain applied from the gate voltage is negligible. So it's completely independent from other parameters in the Hamiltonian strain. This is inside a cryostat that goes to very low temperature, very high magnetic fields, and we can apply basically, this is on a silicon chip which you might think shatters, and it does if you bend it too much, but the trick is that we're using long cantilever arms. So this is a very thin chip of silicon, so you can flex it a little bit, and by flexing it just a little bit, you can stretch this by about 1 nanometer. And since our devices are short, this corresponds to 1 to 10% strain, depending on how long our devices are. So that's the range roughly that we're exploring. And this is a bit how some of these things look like, although it's tough to see the sample inside this construct. This is basically the screw is here, this block rotates inside a fork, and all this has to be decoupled, the mechanics and the electronics, because we don't want to heat things up, we don't want, of course, the wires to get tangled up, and there's a whole sort of art to building assemblies. Now, to make sure the motion works well, what we did is calibration with just tunnel junction. So we use gold tunnel junction, and just the electron flow across a vacuum gap is exponential with displacement. So with these exponential, we can do very good fit and actually see that the motion is very smooth. And also that it's extremely stable. If you just park at one position for the motor and you wait, you get basically stability that's order of much less than 1 picometer. Okay? It sounds crazy, but why it's so stable is because of you're pushing this way, but you're stretching this way. So you have a huge reduction factor in any vibration from this sort of Mongo construct. So that's important to us because we want very stable experiments. Here's an example of initial data we have. This device wasn't perfect with its orientation, but it was pretty good. And we can see Fabry Pro interferences again. Those told us that it's a ballistic device. And then if you apply the strain to it, you can see that current goes down. And also the direct point is shifting. Both of these things match qualitatively with the modeling that we have. In this case, we only applied about 1% strain because it was a 100 nanometer long flake. So that's why the effect is sort of modest, but that also matches with the modeling. And those curves are just basically extracted into the lines, but at different gate voltages. So at all gate voltages, you can see that the conductance goes down. And definitely, because the range of strain is small, there's some noise, but there's a factor of 40% decrease or something in conductance. So we think that we can basically, by going to this shorter devices and building a few more devices so we have different crystal orientation, demonstrate that we can turn off this current and build quantum string transistor. We also saw similar effects on quantum dots. So if you have a device, in this case, we used the electromigration procedure. So the width was only about 10 nanometer and the length 40 nanometer. So those make quantum dots. And we saw that the energy levels in the quantum dots could be manipulated with strain. This we don't fully understand, but the idea is that the energy level in a graphene quantum dot depends on the path of the electrons. It depends how far the electron travels before it exits the dot. And if you change the angle of the injection, the way that basically the length of the path to exiting the dot changes. So that's something we'd like to be able to model theoretically. We have some ideas, but it's not there. But the fact it's fully reproducible going forward and backward, we can split some levels and merge some levels, and it looks a lot like, for example, some of the degeneracy that are in the Hamilton. So to conclude, we think there's a lot of fun, rich physics in the coupling between the mechanics and electronics in nanosystems, especially in the quantum range, a regime that hasn't been explored. And we think that carbon devices are a good place to do this work experimentally. We've built 10 to 100 nanometer electromechanical devices in both nanotubes and graphene. And not only are the channels ballistic, but the contacts are, which is important for our modeling and our understanding of the system. One example of device we built is in a nanotube. We could build 2-in-1 quantum devices where we, for example, have ballistic wires and a quantum dot. We can switch between the two in the same device. We made resonators with basically out of, for example, flexural mode resonators. And now we're working on making strain-dependent conductor, strain-dependent transistors in graphene. Thank you very much for your time. Those are my students.
Questions?
So you talked about bending briefly, and I was wondering if there's some sort of time, how long the device lasts at those oscillations. Is there like a concern for fatigue at that length scale at all?
No,
or
the devices are perfect. They can go on forever. As long as you don't. The problem is electrostatic shocks, right? So in the winter, you have to be careful. The students, they always wear a grounding strap. In fact, commercial ones are not often good enough, so we have basically a piece of metal. But it's kind of dangerous. So it's like working like your feet in the water, right? So that, anyway, there's some safety we try to address, but you have to be careful. But the electrostatic grounding is very important because basically these are tiny fuses,
right?
We engineer them to be ridiculously sensitive, so then they are. And if you don't explode them, they're good forever. You can bake them, right? At some point they'll get contaminated, but you just heat them up, you'll absorb contamination, and they're extremely robust. It's very impressive. I mean, you apply volts in these devices, but they're only 10 nanometer long, so that's enormous electric fields. 10 to the 9 volt per meter amount of field.
Actually, I might have missed it. So how is the phonon related to the strain?
How's the what?
How are the phonons related to the strain?
It's a time-dependent strain, basically, right? So you can think of the phonon wave shape as, you know, it's a local strain formation. I mean, it's just a phonon is just a motion of the lattice, right? And that's how we describe strain. Right?
So would that depend on the size of the graphene that you're using?
Well, it depends on the phonon modes. I mean, one thing that is not discussed here, for example, is that this idea that the coupling between the phonons and the electrons are actually how much they couple with each other is strain tunable as well. So you could, with strain, make the two decoupled or coupled. So that's a very interesting thing in terms of, for example, thermalizing the electrons, making heat management devices. But, you know, I mean, it's a cartoonish picture here, but let me just go back. I don't know if I can scroll through this. It's at the very beginning of the ring, but hopefully you scroll through it. So it's basically just, I mean, this cartoon thing. It's not a cartoon, actually, it's an exact picture, but there's a lot of details that are not shown here. But you can think of strain basically as being just a gauge field, A field, and this is linearly proportional to strain. And if you just time differentiate it, you know, you create electric field. So basically, of course, in a phonon, you have a position-dependent strain. That's the thing, right? So you're going to have a strain which is position-dependent and time-dependent, as opposed to having just a uniform strain everywhere. But it can be, if you want to use this kind of language, it's one thing. You don't have to use this language. Of course, you can just use standard second quantization for phonons. But what's nice is you can, with the strain, you can have a DC and an AC superposed. So you can have the phonon coupling to the electrons. And with the DC strain, you can change the dispersion relation of the phonons, right? So the dominant phonon mode in graphene at low energy is this out-of-plane mode, but it has a quadratic dispersion. And if you stretch it, actually, you can make the dispersion linear. And that actually changes the density of state, how many phonons are available. So that can change a lot, actually, how they couple with the electrons and how much heat can be flowed in the system. So you can reduce a lot, for example, the heat conductivity with strain, supposedly. It's not been verified.
So in your experiments, what's the dispersion amount that you do?
Well, in this case, we didn't measure phonons, right? We're just looking at the electrons, so we don't have that. It's not that trivial to, well, we can talk after, but I mean, there are a bunch of complications to it.
So for the strain transistor case, right, I mean, one strives to have very well reproducible gap usually and so on, right? So the strain transistor philosophy, it seems to be, how to say, depend all the time on the details, the way it's done, right? I mean, you do not know, you have to have a zigzag component of the strain for sure to open the gap, right? And one is not sure. And then, I mean, can you achieve, like, every time you have this gap?
Well, there's, you mean, I understand, you don't mean actual, you don't mean that gap, you mean that, basically when you model the transmission coefficient, what strain
you want it reproducible and always to be the same,
but
whereas so far it looks like it's never the same and it's completely irreproducible, right? So,
yes and no, because the beauty is because you tune fully the Hamiltonian, to prove everything you need one device. So because if you can cross-check things, right? You can change the charge density, you can change the strain, you can change the temperature, all within the same device. You can change the magnetic field. So within one device, you know, with only one fit parameter, which is the edge orientation, which you don't know, you can prove that it's self-consistent. So if you prove in one device it's fully self-consistent, another device fully self-consistent, you do that for a few devices, and then you show on a curve that statistically you get a random orientation of the edge. I mean, it's bulletproof. But to do that, basically, we have fabrication issues. That's really what's come down to. If you want to make extremely wide devices that are very short, it's not completely trivial fabrication because we also need the contact to be suspended with some length. And so this, so really the problem is not our capability to the geometry. It's really how many devices can we make, how quickly. It's
Mhm.
really the problem, because I think a single device can be extremely powerful in improving the whole thing
Mhm.
if it's harvested properly. Because these live for a long time. There's so many things you can.
And I guess you like this fact that if you change the voltage, you change the chemical potential across these PN things, and you actually affect the transmission.
No.
voltage.
This is fixed. So,
That's
to
fixed?
change the PN thing, you need to bake it. You need to apply
Ah,
volts
okay,
to the
to
system,
volt,
right?
okay.
So then you call this, it's fixed, but it's
So the
something.
chemical potential along the junction between the strain and the strain case is fixed.
It's fixed.
Okay, okay.
It's fixed. So this is something you can change, but it's like reinitiating your device, if you will, right?
Mhm.
So for example, I could warm up the device. It will get all full of oxygen.
But the result depends on that, right? So the result is sensitive to this.
Yes, it is. It does. But that is a tunable parameter. So you can basically each time warm it up, bring back the chemical potential to initial point, and rebake it, make it different. So in fact, it's like many devices in one again. So it's another fully tunable parameter. So that's okay. In fact, it's just manpower. I don't think there's any problem there. It took a long time to get here, but at this point, I think the project is fine. What's also nice is that this is not an instrument that I think anyone else has at this time. So I don't think anyone else can do this experiment in this way. They might do otherwise.
Okay.
Yeah, well, I have a couple of questions, but, so first of all, you say you're tuning this electron-photon interaction strength over large ranges, right? So don't you
That could be done in principle. We didn't do the tuning of the
okay,
electron
so you don't get to the point where you can no longer treat it as a perturbation, or you need a completely different Hamiltonian?
There's one case where we see a hint of that. Well, we have some unpublished data in nanotubes where we did see the formation of what we think are polarons. So that's what you're talking about.
Yeah.
So that's, I think it would be just after this. That's the two that's here. So that's basically this idea that if you have very strong coupling, you can, for example, renormalize. You have a new ground state, basically, right? And it's made of polarons. It's not made of vibrons. It's not made of electrons. The quasi-particles are actually, entangled states of the two, mechanical and electronic degrees of freedom. So we see evidence for this. For example, we see that there's a big change in the charging energy, and then if we warm up, this goes away, right? Which you expect because you basically kill the interaction strength with thermal excitation. So it looks okay, but it's only one device, so we don't have a bulletproof proof of that. But that's something that's predicted, and the parameters match the theory. No one has made devices at this scale, basically. So we think that's one of the examples where we might have achieved that regime, but we haven't really explored that regime.
And that's a single carbon nanotube,
Yes.
not a quantum dot.
It's a quantum dot. It's a carbon nanotube that has electrostatic barriers at the two ends, right? So it's about 50 nanometer long. You can think of it looks like this, right? So it's just a tube like that. It's about 50 nanometer long.
That's why you talk about vibrons instead of phonons.
Yeah, well, by vibrons, all we mean is basically you don't have an infinite boundary condition, right? You have a clamped beam, so it's it's
We
like
have
a beam.
students in that class, that's why I'm
Yeah.
asking.
Yeah.
I'm teaching this right now, so you're helping me.
Yeah, it's a quantum of a beam instead of an infinite crystal. So
I'll go back to the graph that you show. I like the other graph. You show VP versus VG.
there's a lot of such graphs. Which
No,
graph?
the one is just before you flip to here.
This one?
The one with color.
This one?
No.
I'm not
The
sure.
one that, the one when she was asking the question you were showing.
Well, that's the.
That's
the one.
Okay. Now, I'm trying to understand this VG versus VT. So you apply a gate voltage, then you sweep bias voltage.
They're all. I mean, it's a two-dimensional map, so everything is swept, right? So it's like a 2D grid.
Okay.
So
What is the vertical? What is the z-axis? Is the current?
yeah, that's the current. So it's here, right? In color. So I mean, the
Oh,
direction
so
of the
that's the
current.
color code.
Yeah. So the current in nanoamps between 20 and minus 20. Minus 20 just means going towards the source, and plus 20 going towards the drain.
Oh, okay, so the blue, red
It's the
color
same
is
thing, you
just,
could change, you could make
arbitrary.
the two red, it's fine, like it's just a direction of the current.
Okay, the basic. Okay, yeah, thank you, thank you.
Other questions?
And one more. So also for the students in the room. So if you were to compare ballistic transport, just ballistic, okay, not the absence of strain, in these graphene layers with the ones in the two-dimensional gallium arsenide systems, or whatever other semiconductor system has been observed typically in the past, what would you say are the differences? Like,
Well, there are a number of differences. So the first one big difference is the density of states available, and it depends a bit how wide is your thing. You're talking about a point contact, or I'm not sure what you. Okay, so the density of state might matter because you have a linear. The big difference will come all from the dispersion relation. Here you have a linear relationship between energy and momentum. In the other case, you have a quadratic relationship. So how many states are available at each energy is not the same, and also the way, if you want to look at transport, you always want to match, wave functions at the edges of the system, right? So when you go from, whatever, part 1 of the problem, like one, potential, to part 2 to part 3, which has different potential. And to get transmission in Schrodinger, you basically have to match the wave function and the derivative of the wave function, because basically it's second order momentum, right? You need 2 boundary conditions. So you're going to have to match psi in portion 1 of the world and psi in portion 2 of the world, but also the deep psi dx, let's say, and deep psi dx. In graphene, you only need to match the wave function, not the derivative, because you only have a first order differential equation, right? So that actually changes the equation you have to solve, and also it will change a lot the shape of the transmission. If you want to calculate the transmission, it'll look very different. Here we give an analogy with, basically you can convert this in a language where you think of angles and so on, but it's not necessary to do that. You think of basically now the modes in the system as either being real or imaginary propagating mode, and you can calculate if they transmit or not once they get across. Most of the differences are technical at some point, but the initial thing is that really the equation you solve is different. It's Dirac instead of Schrodinger.
It would be harder to achieve ballistic transport in gallium arsenide, right? Or
It's quite easy because they've made beautiful structures, right? Before they did amazing structures, it was harder.
Right.
You could do it in quantum point contacts. You just made very narrow channels.
right, full planet channel.
Yeah, the boundary condition is different also with the edges here. Like the edge boundary condition is much tougher in graphene to deal with.
you can see it in heterostructures as well. That's where it was first observed, I think.
Yeah.
Pretty easy.
This reduction in the charging energy, should we think of it in terms of the electrons, which become polarons, sharing this common distortion? Is it essentially a polaron pairing?
Is it ball? I don't think I would say that. The way you can think of it is that basically the wave function is a mechanical electronic part that basically you're trying to inject this electron, and there's now no overlap with the wave function that's for odd charge numbers, right? So for odd charge numbers, the mechanical conformation, for example, would be different than for even charge numbers in terms of the shape of the object, right? The actual number of polarons in the system. So the overlap of the wave function of the injected electron, it becomes 0 basically, and then so you can't have some of the odd charge states. You basically don't have any transmission for that. I don't know how. Okay. In a sense, I think you're right that it's a pairing mechanism, but I'm not sure how to say it in a few clear words, I guess. What was your? Can you rephrase your question, perhaps? Maybe I
Well,
missed it.
I'm trying to understand if there's an energy lowering because two electrons sharing a distortion has a lower energy than one electron with a distortion times 2.
Yeah, I mean, it's a bit that you have to do a transform. It's a little bit like when you do superconductivity, right?
Well, that's what I'm getting at.
So that's what you do.
should
Yeah,
we-
I think the transforms is very similar. The idea is that you have to be careful. It's not a concept or anything like that, but it's a one-dimensional system. The analogy has some limits, but yes, in terms of thinking of new quasi-particle formation, I think you're correct that the ground state is made of pairs of particles. You can have one pair, two pair, three pairs, and those are composite particles made of byproducts and electrons. But I'm not sure I can explain it in a very casual way. I mean, this is preliminary data. Honestly, we haven't written the manuscript. That's often when you answer these subtleties. But anyway, if you have perhaps a more pointed question, I can try again. But I'm not sure if
I don't have a question, but I have a comment. It reminds me of this work that Tinkham used to do, where he had the superconducting ion. And so rather than an island, where you'd have some finite number of electrons that would start to form the superconducting correlate, the pairing correlations. Here you have a tube, a nanotube, rather than some metallic island.
Yeah, I mean, the answer to your question is basically this manuscript. That's the theory. I mean, there's also, in fact, the analogy is a bit easier with the Kondo effect because it's a 1D system. So, but it's the same. Instead of having, you're thinking of coupling with a spin degree freedom, you're coupling with the charge degree of freedom. Yeah. But okay, maybe that's fine.
All right, one last question. I have a short one. So when you're actually trying to figure out what the amount of strain that you're applying is, and do you get this by measuring the effective separation between the leads via these interference fringes, or how do you know that you have 1.2% strain?
So it's an estimate, but it's a good estimate. So of course, once you have the data, you can cross-correlate. But basically, we build tunnel junctions on all of our chips. And so we have gold tunnel junctions nearby. And then we, on the same system, right, we actually measure the tunnel current with them. And that's how we calibrate, because that is a very robust feature, the dependence of tunnel current with displacement. It also turns out that we understand the geometry of a system pretty well, like the length of the contact and so on. And this actually gives us a very good, it's consistent with what we measure for tunnel junctions. So, but yeah, it is not, what's the beauty here is not necessarily the number of the strain, it's the fact that it's tunable. So you know that you can go from 0 to something, whether that something is 1.5 or 1.3% is not that big a deal if you can continuously map it out. If you only had a few points, then the number we would care a lot about. So that's what we like, that it's tunable. That's a really important feature for us to understand what's going on.
Okay, are there any other questions? Let's thank Professor Champagne again.
Good, and you? No, Professor,
Somewhere between pro and professor. Somewhere between
the professor.
the pro professor.